What's up? I'm Vin, and today I want to solve trig equations by using identities. So these are the trig identities we're going to use, and let's get started. So for the first question here, we want to solve for all values theta. Here's our equation, and here are the trig identities we want to use. Now, the first challenge you're going to run into with questions like this is you want to make sure you choose the correct identity. So generally what you want when you have a quadratic trig equation is you want it all in terms of, let's say, sine and sine squared, or you want it all in terms of cosine and cosine squared. So replacing sine theta is not going to be easy with these identities here. But what we can do is replace cosine squared if we use the first identity. And what we could do is think of this identity here as something that's very flexible. We could move terms around. So what I could do is I could subtract sine squared on both sides, and that allows us to say that cosine squared theta is equal to 1 minus sine squared theta. Okay, so we're just once again rearranging that first equation, and now we're going to use that to get this started. So what we could do first is we can make the substitution. We have 1 plus sine theta. And now this is equal to, we're going to have 2 times, and instead of cosine squared theta, we're going to replace that with 1 minus sine squared theta like this. And now the rest is going to be algebra here. And we're going to distribute the 2. That's going to give us 2 minus 2 sine squared theta. So once we get to this step here, we have 2 sides to this equation. We want to move everything from the right side to the left side. And I want to do that in this case because I prefer to have a positive number in front of the square term. So I'm going to add 2 sine squared to both sides first. And then all in the same step, what we could do is we could subtract 2 on both sides. So now the right side is going to cancel out completely. So on the right side, we're going to be equal to 0. But now on the left side, we're going to have 2 sine squared theta. And then we have a plus sine theta. And then the other terms to combine here, we have 1 minus 2, which makes negative 1. So now that we have this new equation here, the next thing that jumps into mind is factoring quadratic equations. So while technically this is a quadratic trig equation, the thing that comes to mind is I think of 2x squared plus 1x minus 1. And this resembles this expression here quite a bit. And the technique to factoring this type of expression is the AC method, where we refer to a as the coefficient of x squared, b is the coefficient of x, and c is the constant at the end. So the AC term here, 2 times negative 1, will make negative 2, and the b term, the coefficient of x, is invisible, and it's the number 1. And now we just have to search for 2 numbers that have a product of negative 2 and a sum of positive 1. And those numbers would be 2 and minus 1. So now how do we apply that here? Well, we're going to break up the middle term using these numbers that we found. So we're going to have, instead of plus 1 sine theta, we're going to call that plus 2 sine theta minus 1 sine theta. But once again, we'll keep that 1 invisible. And we have minus 1 equal to 0. So now the next technique that we need here is factoring by grouping. So we're going to go ahead and factor out the greatest common factor, and we're going to have 2 sine theta on the first 2 terms, and we'll be left with, on the inside, we'll have sine theta plus 1. And if you ever want to check, you could always distribute to see that you did this correctly. And now for the second 2 terms here, it would make a lot of sense to factor out a minus 1, because then on the inside we'd be left with sine theta plus 1, and it's a good sign when these 2 terms match here. And now going from this step, we're going to factor out the match. So we have sine theta plus 1. And now in the other set of parentheses, we'll have 2 sine theta minus 1. And this is all equal to 0. So now we'll set each factor equal to 0. We're going to set sine theta plus 1 equal to 0. And we're going to set the second factor, 2 sine theta minus 1 equal to 0. Now the first one, when we solve for sine theta, we're going to get sine theta equals negative 1. And there's a few ways you could go forward with this. If you're doing this without a calculator, then you really have to know the unit circle. And what you're asking yourself is, for what angle is sine negative 1? I always think of sine as the y value on the unit circle, and the y value is negative 1 down at an angle of 3 pi over 2 radians, which I'll just make this a little bit neater. So from this, I could say that theta is equal to 3 pi over 2 radians. Another way of getting this, you could just use the calculator and say sine inverse of negative 1. And if you're doing this in degree mode, it's going to tell you 270 degrees. And then you could just convert 270 degrees to radians. But what we have so far is theta equals 3 pi over 2. Now for the next equation, we have a little bit of algebra to do here. We're just going to add 1 to both sides. So we have 2 sine theta equals 1. And then we just divide both sides by 2. And that's going to give us, we're going to have sine theta is equal to a half. And for this part here, we have to know a little bit about finding trig values in all 4 quadrants. So we have sine theta equals positive 1/2, which means quadrant 3 and quadrant 4 are out. Sine is only positive in quadrants 1 and 2. And then here we just have to think, what would be our reference angle? Well, sine is equal to 1/2 at 30 degrees, or we could say pi over 6 radians. So here's our reference angle, and it's also one of our solutions. We have pi over 6 as one of our solutions. And then for the second solution in quadrant 2, we would do the second quadrant solution, we could say, is pi minus pi over 6. And what we have here, this is going to be 5 pi over 6. So here's our solutions. But one thing to be mindful of is that for this question, they said to find all solutions theta. So I want to be very thorough here and make sure that we list them all. So what we're going to say is we have 3 pi over 2, but be mindful that we could get to this angle again if we go another 360 degrees or another 2 pi radians. So we're going to say 3 pi over 2 plus 2 pi times k, where k is any whole number, any integer. And that includes 0 and negatives, because I could spin in the positive direction or I could spin in the negative direction. And I just spun this way is actually going in the negative direction. Positive direction would be going counterclockwise. So that would be for the 3 pi over 2 solution. But then I could also say we have pi over 6 plus we would add in the 2 pi k for this, and then comma, and we'll just throw that in underneath. We have 5 pi over 6 also plus 2 pi times k. And once again, we have to specify here that k is going to be an integer. So k is any integer. And then that would cover all the solutions to that original equation. So for the second question here, we'll limit ourselves between 0 and 2 pi radians. And what jumps out at me immediately in this equation when I look at all these identities is the double angle. Because there's no nice way to solve an equation with sine and cosine where one of them has a double angle. So I almost always will try to get rid of the double angle. So that means I'm going to use this equation here in the fourth line. So we'll go ahead and do that. Instead of calling this sine 2 theta plus cosine theta, we're going to replace sine 2 theta with, we're going to have 2 sine theta times cosine theta. So once again, we're making a substitution for this piece here. And then we could just tack on the plus cosine theta and set this all equal to 0. So now from this step, we could just factor out the greatest common factor, which is cosine theta. And I have cosine theta, but now I'm left with 2 sine theta, and then I'm left with plus 1 after we factor out cosine from the second term. And this is all equal to 0. So now, same process as before, we set each factor equal to 0. And what we have is we have cosine theta equals 0, and we have 2 sine theta plus 1 is equal to 0. So for the first equation here, I'm thinking of the unit circle again, but just know cosine corresponds to the x values on the unit circle. So what I'm really thinking about for this one is if I want to know when is cosine equal to 0, I look for when is the x values on the unit circle equal to 0. And that's going to be true at pi over 2 radians, and it's also going to be true at 3 pi over 2 radians. So kind of in the north and south position here. So then if we have to actually write out a solution here, what we're going to have is we're going to have theta equals, and for this part, we have pi over 2, and then we have 3 pi over 2 for the second solution. But now we could shift our focus to the second equation. So this one we could start by subtracting 1 on both sides, and we'll have 2 sine theta equals negative 1. Now we just divide both sides by 2, and that's going to give us sine theta is equal to negative 1/2. So now we have to use our prerequisite skill of knowing the quadrants for the trig functions. So we have ASTC, and remember, all trig functions are positive in quadrant 1, only sine is positive in quadrant 2, and since sine theta is negative 1/2, that means our two solutions for theta have to lie in quadrants 3 and 4. And what we should find next here is our reference angle. So then for this part, we just think when is sine equal to positive 1/2? And that would be at an angle of pi over 6. So that tells us our reference angle is pi over 6. But we have to be careful. This is not a solution. This is a tool to help us find our solution. So what we have is our theta from the second equation. We could find our quadrant 3 solution. And our quadrant 3 solution we get by going from standard position, we're going pi radians plus we're going pi over 6. So if we do pi plus pi over 6, that's going to work out to 7 pi over 6. So here's our quadrant 3 solution. And then for our quadrant 4 solution, we're going 2 pi, so we're going full circle, except we're going to fall short pi over 6 radians. That's our reference angle. So here we're doing 2 pi minus pi over 6. And if I'm doing that in my head, I'm saying 12 pi over 6 minus pi over 6 is 11 pi over 6. So we're just doing that here. And then we'll just write all our solutions together. So all of our solutions at the end, we have theta equals, and we've got pi over 2. And then we could write them in order. The next one would be 7 pi over 6. And then after 7 pi over 6, we would have 3 pi over 2. And then after 3 pi over 2, the last one would be 11 pi over 6. Okay, for the last question here, we're finding theta. Theta is between 0 and 2 pi radians, and we have this equation here. Now, once again, the double angle is the piece that I'm always looking to replace first. And now we have to be strategic because cosine 2 theta could be expressed three ways. We could say cosine squared minus sine squared, 1 minus 2 sine squared, and then 2 cosine squared minus 1. But remember, the trick is that you want it to match the other trig function. So since we have a sine squared, I'm going to go with the version that only has a sine squared attached, which is the middle one here. So we're going to use the fact that we could say cosine of 2 theta is equal to 1 minus 2 sine squared theta. So this is the one that we're going to want here to use. And what we have is we have 2 sine squared theta equals, and then we have 2 plus cosine of 2 theta. Once again, we're using this version. So we have 2 plus, and we have 1 minus 2 sine squared theta like this. So now from this step, we have 2 sine squared theta. And now this is going to be equal to 2 plus 1 is equal to 3. And be mindful, there's nothing outside the parentheses here, and this parentheses is not being raised to an exponent. So we could just drop the parentheses, and we could say 2 plus 1 is 3, and we have minus 2 sine squared theta like this. But now we'll move everything to one side, and I prefer to move this over to the other side so that we have a positive in front of our square term. So we have plus 2 sine squared like this, and then all in one step we could just subtract 3 on both sides. So now on the right side we're going to have 0. So we have 0 on the right, and then 2 sine squared plus 2 sine squared is going to make 4 sine squared theta. And now we just tack on the minus 3. Now from this step, we just have to do a little bit of algebra. So we're going to add 3 to both sides, and that's going to cancel out these two terms. And we've got 4 sine squared theta equals 3. We'll divide both sides by 4, and now we get to this step here, and there's a little trap set for us. We have sine squared theta equals 3 over 4. So a common mistake here is students will take the square root of both sides, and they'll say something like this. They'll say sine theta equals the square root of the top, we could just say square root of 3, over the square root of 4 is 2. So they do this, but this is a very dangerous trap. You have to be careful. The idea that the square root of x squared equals x is something that you should abandon immediately. The square root of x squared, we could say, is plus or minus x. We can't just say x. Another way of saying this is the square root of x squared is absolute value x, but almost everyone, when they're just doing algebra, will write the plus or minus so that it could just get to solving the equation for all values. So what we have here is we're going to say sine theta equals plus or minus square root of 3 over 2. And that way we don't miss any solutions, because otherwise we would only find 2 instead of all 4 solutions. So now what we have is we have sine theta equals square root of 3 over 2. And we have the other equation, sine theta equals minus square root of 3 over 2. And for this, we're going to have the same reference angle, because if you notice, the absolute value of both of these ratios are equal. So here, what we have is the reference angle. We just have to think, when is sine equal to square root 3 over 2? And that would be 60 degrees. And we could say 60 degrees in radians as pi over 3 radians. And now, for this part, sine theta is positive root 3 over 2, tells us we could be in quadrants 1 and 2. But notice for the second equation, sine theta equals negative root 3 over 2, would put these two solutions in quadrants 3 and 4. So we're really going to be hitting all 4 quadrants with a reference angle of pi over 3. So we could just write out all our solutions at once. We have our quadrant 1 solution is equal to the reference angle, which is pi over 3. And then if we have a reference angle of pi over 3 in quadrant 2, so here's our quadrant 1 solution. In quadrant 2, we would do pi minus pi over 3, which would be 2 pi over 3. And then if we go into quadrant 3, we would do pi plus pi over 3. And if you do pi plus pi over 3, that's going to make 4 pi over 3. And then the final solution in quadrant 4, you would do 2 pi minus pi over 3, and that would give you 5 pi over 3. So here are the 4 solutions to the last example.